Well, good evening. I'm sorry it's 5 minutes late getting started. I had to go down to the hall, down the hall for a minute, and had so much drainage that I had to go back. So let's pick up from the current slide. And we've had a question. Let me get my pen set up. Okay. Similar to number 10 on the second test, this is number 5 in problem set 8.4. This is going page 224. Okay. Problem set 8.4, number 5. Now we'll expand a little bit what we're doing here. Here we have a 0.175 pound ball is thrown upward. Now let's time out just a minute. On your number 10 on your test, it gives you a 55.0 gram bullet fired vertically with an initial velocity of 123 meters per second. Okay? Now all the questions it's asking there deal with velocity, height, and velocity again when it hits the ground. Okay? There's no place in there you have to use the mass. Okay? So when this says a 0.175 pound ball is thrown upward with an initial velocity of 75, so here's, you are on the ground down here, and you're throwing the ball straight up, okay, straight up, and the ball is 0.5, the mass, no, this is the weight of the ball, F sub W. Let me clean that up a little bit, because this now is in the U.S. customary system, it's not the SI system. The weight of the ball is 0.175 pounds, which isn't a very heavy ball. Okay, thrown upward with an initial velocity, so V sub I is equal to 75 feet per second. Feet per second. I wrote it right down that as feet, didn't I? Okay. 75.0 feet per second. What is the maximum height reached by the ball? Okay. Now, and that's also, that's the B part of your question. Yes, sir. Okay. Before we get to that part, let's think about the ball here you're throwing straight upward. Now somewhere up here it reaches its maximum height. Okay? And the A part says, what's the velocity of the ball at the highest point? 0. Okay, you got that one. Okay. They didn't ask that here, but it would be the same here. Okay? Now, the next part says, what is the maximum height reached by the ball? Now, that let's see. Now, you remember our little formula, the one that's on page 219. That is talking about a pile driver that's being dropped, and initial velocity up here is 0, right, when you drop it. And you're talking about what is velocity right before it hits. Okay? Well, that all depends on how high you drop it fell from, right? So, when it says how high does it go, it's sort of a reverse problem. This one comes from the pile driver's up here, you drop it, and it goes down and reaches velocity down here. Okay, now you're throwing the ball up, and it's going up and reaching a velocity of 0 up here, right? So it's the same problem, just flipped over. So the h in this formula here is the same height. That's going to be the maximum height reached.
Let me ask you a question.
Yeah.
Okay. When it's going up, what I said, I was listening to you over the weekend when you gave us, okay, going up is my positive. So I put a positive 0. Then
Okay.
down, I put negative 0.
Okay, wait. 0 is neither positive or negative, so it doesn't matter what you put on a 0.
Okay.
So at the height, the A part, the sign doesn't matter if you got that number in there, okay? So what I was going to say is, what we have here is V is equal to the square root of 2GH. Now we're looking for the H, maximum height, right? Aren't we? So we need to solve that equation for H. So what's the first thing we got to get rid of? What's mucking up that issue there?
The square root.
Square root. And how do you undo a square root? Well, not quite. It's close. Just leave off the root part. Square it. Square both sides. If you square both sides, you get V squared is equal to 2GH. See, squaring a square root undoes the square root. It disappears. But on the other side, you squared it, right? Now, we're still wanting to solve for H, so let's divide both sides by 2G. Okay? And then the 2G's go away. So now you got the height, and this height is going to be in feet because your velocity was given in 75.0 feet per second, but you're going to have to square that, both the numbers and the units, and you got to divide by 2. Now, what is G in the U.S. customary system? Yeah, the acceleration due to gravity. And what is the value of it in U.S. customary system?
9.8.
No, that's in the SI system. That's meters per second squared. We're dealing with feet. Says, yes, 32.2 feet per second squared. All right? So, pull out your handy-dandy little calculators. And you square 75. I can't do that in my head. It's going to be something less than 5,000. 75 squared. What does that give you? Maybe about 4,000. 4,500. That's 75 squared. Okay, now not square root, squared. It's certainly not that. Okay. Get rid of all that. 75. Okay, you're squaring. Now, let me. Yeah, that's the key. See, that's the square root key.
Oh.
That's the square root key. There's the square. And it gives you what?
56.25.
Oh, yeah, great. Something greater than 5,000. I don't know what I was thinking. Something greater than 5,000. So that's 56.25. Okay. Now I'm going to write it down. 50. You don't have to. 56.25, and that's feet squared because you squared the units as well over second squared, and we're going to divide that by 2 times 32.2 feet per second squared, And notice the per second squareds go out. One of the feet go out, and it leaves you with feet. That's a great measure for height. So your units make sense, so you feel really good about this. So do your 5625, or was it 725 or 75? 25. Divide it by 2, and then divide again by, or divide it by 64.4. That's 2 times 32. 32.2. Divide it by 64.4. Yeah. 43.6. Ooh, that's too much, isn't it? Wait. No, that sounds right. Okay, say again. Say again. 43. Okay, 43 point. Say again. Do you want me to round it? Okay, yeah. And what did you say? 0.7. That sounds good. Feet. So that's how high it's going. Okay? Notice you didn't use the weight of the ball at all. Now let's just check and make sure everything's copacetic here, and we are getting the same thing that we do in the back of the book. This is 8.4, number 5, 80, whoa, wait. $75 squared divided by 64. Yeah, I was thinking, yeah, okay. It's got to be more than 43. I've got it. Okay. Did you divide by 32.2 or?
It'll be 44 because when you round it up.
Okay. Tell me what you divided by. 5625 divided by 64.4. Is that what you did?
Yes, sir. And this is what it gave me.
Okay. This doesn't seem right. Okay. Should be a much. What was your answer? 625. 5625 divided by 64.4. Right? Okay. And how do you get an answer? Hit it, answer again. Yeah, that's the one.
Okay.
I knew the number had to be bigger than that. Let me mark Haley here. All right. Now, and what did, let me erase this number we had before. And what did that come out being?
87.3.
87.3 feet. And that's what I think it was in the back of the book, didn't I say?
Yes, sir.
Okay. All right. Now, we're doing problem 5 on page 224, problem set 8.4. Whoops, I turned too many pages. Nope, not enough pages. There we go. All right, so that was the only part of question 5. There is another part of your question 10. Okay? If you threw this ball up into the air with an initial velocity of 75 feet per second, okay? That's a pretty hard throw, okay? Throwing it up there, and as it goes up, it's decreasing speed as it goes because the acceleration due to gravity is downward. So it's going to make it slow down, because every second it loses a velocity of 32.2 feet per second. So in the first second, it's already down to 42.8 feet per second. And then in the next second, it's dropped again to around 16 point whatever seconds. And then somewhere in the next second, it actually slows to a stop. Okay? And then what does it do? Does it just hang there? No. It starts coming back down. And as it comes down, it picks up speed at the same rate it was losing speed going up, right? So guess what speed it's going to have at the bottom? Really? I thought you said it was gaining speed as it came down. Because the acceleration due to gravity is downward. When it was at the top, it was at 0. So it can't be coming down and still be at 0. It would have just stayed up there if it's still 0. When it's coming down, it's picking up speed. Every second is picking up 32.2 feet per second. Only the one in your book is meters per second. So yours, as it's going up, every second it goes up, it loses speed at 9.8 meters per second. So in the first second, it's down to about 113.2 meters per second. And the next one, it's going to be, so it's losing speed all the way up until somewhere way up there, somewhere way up there, it stops. And then it starts falling. Now the acceleration of gravity is in the same direction of the motion, so it's increasing the speed every second as it comes down. So guess what the speed is when it reaches the bottom? Okay. If it's increasing speed as it comes down, it can't be 0 at the bottom. Now when it hits the ground, yeah, it's going to stop and go to 0, but just before it hits. You threw it up with a velocity of this one was 75 feet per second. So it loses speed every second it goes up until it reaches 0. And then it starts coming down and starts gaining speed at the same rate that it lost it going up. So what's the speed at the bottom?
0.75?
Yes, it is. 75 feet per second. Okay? Only this is negative because it's going downward.
Okay. That's what I keep trying to say, because I know once it hit the ground.
Yeah, it's going to stop, but yeah, right before it hits. If you're going to catch, well, you don't want to catch a bullet, but if you're going to catch the ball on the way down, it's going to be the same speed as it did when you threw it going up. Now that, and I'll give you this as an illustration, I don't know if you've seen, especially in third world countries, but sometimes it happens in our country when people go out celebrating something, firing weapons into the air. That's one of the dumbest things you can do.
Because what goes up must come down.
You're absolutely right, and it comes down at almost the same speed. So if you fire that bullet up in the air, whatever speed it has, leaving the muzzle of that gun, then it's going to lose that speed as it goes up at 9.8 meters per second, or 32.2 feet per second. Lose speed as it goes up, but then when it's coming back down, it's going to gain speed at the same rate. So if you fired it straight up, absolutely straight up, then it's going to go up there, stop, and come down. You'd better move, because when it comes back down, it's going to be just the same speed as when you fired it. It's just in the opposite direction. And you could, if you're in the same spot, you could be dead, because it's just like turning the gun and firing straight at your own head. Now what's even worse, you fire it up at an angle, and then someone over there, he doesn't even know you fired the shot, it may come down and hit them at the same speed that you fired it here. Okay? Now, it was, I think, the very first year we lived in Birmingham. It was within the first couple of years. We saw this story on the television of this couple coming back from somewhere on the interstate. I think they were out there somewhere maybe around Anniston or Gadsden, or not Gadsden, Anniston or Oxford, somewhere around there. They were coming back home. They had the little baby in the club cab, strapped in right where she belonged, of their pickup, and they were coming home, and they heard something, sounded like a little pop, and they wondered, what in the world is that? They turned back. The baby looked like she was asleep. So they just kept on driving until they got home, and they went to take her out, and a bullet had come right through the back windshield and gone into the back of her head. Now, the bullet hadn't been fired at her at all. Someone had shot into the air miles away, and they don't know who it was, and it just happened to go up and then come back down, and just by worst luck possible came in and hit right in the back. Like you said, everything that goes up comes back down. The rest of that saying should be at the same speed it was launched, because that is absolutely true. So that should answer your C part, right? Okay. Good deal. Any other questions? All right. Now, last time, I hate to say this, almost felt like a wasted class to me, because it's all these terminology that you really don't have to know, but they have it at the front of this chapter, so I feel like we need to go over it.
You're on chapter 9?
No, chapter 12. We did 5, 8, and then 12. Okay? So I'm going to erase this problem here. Is that okay?
Yes.
All right. Now, we were going over all these words and what these are. If you go back several pages, these are properties of solids. And these are just all these different properties of solids. Remember, we said there were 3 phases of matter. The book calls them states of matter. We actually said there are really 4. Solids, liquids, and gases. We're talking about solids now, and these are just properties of solids. The next one we're getting to is this one called tension. Now, that's not like a tension headache. That's not like that, though it does have some similarities. Because what is tension? It's a stress, okay? That could almost sounds like a tension headache. Whoa, my...
What page?
Wait just a second. My power cord just came loose. Now it went back. It's top of page 318. Okay? It's a stress caused by 2 forces acting directly opposite each other. 2 forces acting directly opposite each other. Okay. That's the definition of a stress. And actually, I'm sorry, I'm interrupting the class again. I just happened to think of a couple of announcements. I was going to wait till more people got here, and then once they got here, I forgot to do the announcements. So let me do these. The first is maybe a little silly. It's one of these good news, bad news situations. Okay? The good news is, the bad news is that next Thursday is the 4th of July, and no, that's the good news. For the 4th of July, the bad news is we won't have class. Sorry about that. Okay? The school is closed next Thursday. Now, are any of you taking any classes other than this one? You are? Okay. Do you take any on Wednesdays? No. Yes. Now, I heard this. I haven't seen it on an email yet, so it's not official yet. But I heard that the governor has declared for state employees Friday's also a holiday, because Thursday's the 4th, just to give people a long weekend. She declared Friday a holiday. Well, we take Fridays off in the summer, so in order to accommodate that, now this is what I've heard, but it isn't official yet, that classes may be suspended after noon on Wednesday. So, because we're not here to take advantage of Friday's holiday, so they're going to give us a half day on Wednesday. Now, I heard that. Don't act on that until you see it something officially. You'll meet with your instructors on Monday, right? Okay, let them let you know. If we haven't heard anything by then, I have a feeling it's not really true. This was the secretary telling me. Usually they got the scoop pretty well, but it may be that she got it wrong. Okay, so just wanted to let you know that too. All right. And I don't think we need to make up that class, because the Thursday class, because that's a state holiday. It was already planned in the schedule. Okay, so what is tension? It can be one of two things. Two forces butting heads like this, that's tension. Okay, we'll actually talk about that different next time a little more, but two forces like that, that's definitely tension. Okay? If you're in the middle of that, you feel the tension, okay? You're being stretched in opposite directions. The example of this that they give is the, what do they call it? Tug of war. You know, two teams are pulling in opposite directions on a rope, trying to make the other one give, okay? So that's illustrated in Figure 212. The next one of these properties of solids is compression. Okay, and compression is just about the opposite of tension. It's a stress caused by two forces. Stress caused by two forces acting directly toward each other. Okay, so whereas a tension is away from each other, the compression is toward each other. That's a compression. Now, I'm going to get out of this for just a moment, and actually, this is the easiest way, and we'll go to this one. And here's the figure 1213 in the text. This looks like, have y'all ever been over the Chapelaya, is that what they call it, bridge in north of New Orleans? It just seems like you go across that bridge forever. But they also have them probably in Mobile and Tampa and other places too. Obviously, there's a lot of pressure on that road up above, all the weight of that road and the bridge and everything else. Well, the piling is pushing up, this is going down, so these are pressing against each other. This is a compression. And actually, things get smashed, pushed together. And over time, some of these will start failing a little bit. Okay? This is New Clark Bridge on the Mississippi River. Okay, so I wasn't far off. Okay, now the next of these, and I don't think we got to figure. Oh, this is also showing the column that they showed here. They've illustrated it like this. You got a column here, the force of the piling here, and then the weight of coming here. This is pressing. So this is actually compressing the metal, the concrete, whatever is in between there is a force together. All right. This is one called a shearing force. Okay? This is another property of solids. Oh, and now I have to get my pen back. Okay? Shear. Shearing. It's a stress, all these are stresses, caused by two forces. I can't write. That's ugly. Get my pen back. Where's my pen? Come on, there you are. This. two forces applied in parallel and I'm just going to draw two parallel lines. That stands for the word parallel in opposite directions. Okay. Here's the book. It's a loose leaf book. It looks like it'd be a phone book or a catalog or something like that. And number one, he's pushing down on it a little bit, making the friction grate between it and the table. And then he's pushing on the top half of the book, and that shears the book in one direction, whereas the parallel force, the frictional force on the table in the book, is pushing in the opposite direction. And that distorts the book. That's a shearing force. It's kind of like a compression, except compression are exactly opposite each other. These are opposite each other, but with a distance in between. That's called a shearing force. Okay? They say here, scissors use shearing to cut paper. You don't usually think of it that way, but actually if you think about what do you do with sheep, you shear the sheep. So indeed that sort of is what's going on there. Now here's another one. Oh, and this is the illustration of that. Two forces separated by a distance but going in an opposite direction, that creates a shearing force. Okay? The next one is this one. This is called a torsion. Now that almost sounds like tension. It's not. This is T-O-R, not T-E-N. Torsion. Okay? It's a stress related to a twisting motion. All these are stresses related to a twisting motion. Okay? Now, you're screwing the bolt into, there must be a nut underneath this that you're connecting it to. That is a twisting motion. I'll give you a little bit better illustration of that. How you measure this is not just the twistingness of it, but think of this. Here's the guy's hand out here on the wrench, right? But the bolt is here, right? And as he pulls on the wrench in this direction, the bolt is twisted like this. This pull on the bolt here, on the wrench here, that's in that direction. The displacement from the nut, from the bolt head, is that much. So this is force cross a displacement. This gives you a torsion, a stress related to a twisting motion. We sometimes call it, and I'm going to introduce this, a torque. It's almost like torsion, but it's a torque. T-O-R-Q-U-E. It's a force times a displacement, but not the same as work. This is torque. Now, I think we talked about this back when we introduced the work. Okay? Now, here's the illustration of that. And the symbol for torque or torsion is tau. That's the Greek letter, like our little t, that's their little tau. Okay? Now let's see if the next one. Yeah, here's the next one. Bending. Bending involves both tension and compression. Tension, you go back a page, and compression. Now, how is that? Okay, this guy's sitting on the board. I gave that illustration earlier. If I put a 1x4 across the tables here and started to walk across, and y'all were saying that it's going to break, it's going to bend, it probably would break too. But anyway, why? Think about right where he's sitting. The board is doing like this. So you're compressing the upper side of that board and you're tensioning the lower side of the board. And here's what we mean by that. The forces on the top of the board are pushing together. That's compression. On the lower side of the board, they're being stretched. That's tension. Compression on the top, tension on the bottom. Two forces, opposite directions along the same line. That's tension. Two forces, opposite directions along the same line, but pointing toward each other. That's compression. Okay. Are we almost through with this? Yes. No, not quite, but getting close. One more term here. Okay. We'll get to this one in just a minute. And this term is strain. What in the world is strain? It's the deformation of an object due to the applied force. The deformation, in other words, how is it deformed? My nose is itching like crazy. Of an object because of the force acting on it, due to the applied force. Let me give you another way to say it. Are y'all good English majors? Okay. I think of stress as the verb. The bending, the stretching, the compression, the tension, whatever. That's the verb. The strain is the object of the verb, the direct object, what it's causing. So the stress is the force. The strain is the result of the force, the deformation because of that applied force. Okay? Now, this is try this activity, and you're certainly welcome to do so. It's a pretty simple and sort of fun-looking thing. But if you look at that, if you had marked those blue marks on top and the red marks on bottom exactly equally spaced, but then you bent it like we were talking about before, notice how the reds look like they're closer together and the blues look like they're further apart. Why? The blues are being tensed, tensional force, and the reds are being compressed, the compressional forces. All right. Enough of that. Okay? We'll come back to this very shortly. In fact, I'll go on and leave it there. But let's get out of this and go back to our other slide. Okay. Because here comes our first example in this section. Okay? Example 1, bottom half of page 320. A steel column in a building has a cross-sectional area of 2,500 square centimeters. It's a steel column in a building, so let's just call it this. And this area here is equal to 2,500, and that first zero is significant, square centimeters. Okay? Supports a weight, so this steel column here, okay, is supporting a weight up here. Maybe this is a big beam or something like that. And this weight is this is force due to weight, is 1.5 times 50 times 10 to the 5th newtons. That's 150,000 newtons. Okay? Find the stress on the column. The stress would be a compressional stress. And if you go back and look at your formula, stress is equal to force per unit area. compressional stress in this way, so the stress will be your force, 1.50 times 10 to the 5th. Now, we'll just leave it like it. Newtons divided by, now here we got a problem, Houston. We usually refer to stresses in a term of pascals. Okay? Now, Pascal is a Newton per square meter. We've got square centimeters. So we've got to convert the square centimeters to meters, the square meters. So here again, we've done this several times before. We're converting square centimeters to square meters. And in the middle there, in between, I put the two blanks. The first blank is for numbers, second blank is for units. Always, always, always put the units in their place. So which unit goes where? One goes above the line, one goes below the line. Which one goes where? Okay, units. Which unit goes above the line? You got two units, centimeters and meters. One goes above the line, one goes below the line. Which one goes where? Meters go above it and centimeters go below it. Now that you got the units in their place, now match the numbers with the units. How many meters in a centimeter or how many centimeters in a meter? Come on, think about money. How many cents? Cents in a dollar. Cent is the same prefix as centimeter. How many cents in a dollar? 100. So how many centimeters in a meter? Cents means, milli means 1,000. Cents is 100. 100 centimeters in 1 meter. Okay? But we don't have meters and centimeters, do we? We have square meters and square centimeters. If you're going to square the units, you have to square the numbers as well. Now, 1 squared I can do. That's 1. 100 squared is 4 zeros. You double the number of zeros, so that's 10,000 square centimeters. So, we're going to take this area of 2,500 and divide it by, move the decimal 4 places to the left. And that means you're going to have 0.250 square centimeters. Nope, I just did it. Square meters. Because here this becomes 0.250 square meters. Okay? Now, pull out your handy-dandy calculators and see what that gives you. 1.5 EE or EXP, whichever your calculator has, 5 divided by 0.250 or 0.25. Trying to remember that. It goes something like maybe 0.75 maybe. Uh, 0.6, right? Except that's going to be 6 point. Someone help me out with this. 1.5 divided by 0.25. Is it 6.0? 6.00 times 10 to the 6th. Not newtons. Newton per square meter, you could say that. But what is a Newton per square meter? Pascal. We had that last time. You weren't here, so okay, Pascal. Well, that's a mighty big number. You want to get a smaller number but a bigger unit? You could say 6,000 kilopascals. Move the decimal 3 more places. Or if you wanted even smaller number, bigger unit, that would be 6.00 megapascals. Mega means a million. 10 to the 6 is a million. Okay. Whoa! I think you punched the numbers in wrong. Oh, wait. Did we? No. Yeah, we got the numbers wrong. It's not 10 to the 6th, it's 10 to the 5th. I was going by what you said, sorry about that. 10 to the 5th pascals. And move it 3 places, and then that would be, oh, that's 10 to the 5th pascal. Move it 3 places, and you got 6.00 times 10 to the 2nd kilopascal. Or you could write that as 600 kilopascals. Okay. Either one of those is fine. Okay, is that making sense? Lot of pressure. Almost 1,000,000 pascals. But of course, remember, a pascal is a very, very small unit. Now, did you really get 0.6 in your calculator? If you did, I think I know what you did. I think you did times 10, and then you put the EE or EXP. Don't do that. The scientific notation is 1.5 EE or EXP 5. Don't put times 10, then EE or EXP. To do scientific notation, that takes the place of times 10. EE or EXP, and just hit 5. Okay. Oh. I have to get it so I can see it. Goodness, this is hard. There it is. It's that blue key right there, the EE. So how you do that? What was it? 1.5? 1.5. And don't do times 10. You do the EE set. Second EE, and you see, you get that E there, and then you put 5. Yeah. And you're going to divide that by 0.25. Is that right? Yeah. Hit equal, and you get 600,000. You put it back to scientific notation at 6.00 times 10 to the 5th. All right. Make sense? All right. Robert Hooke was a chemist and physicist in England. He came up with the law governing elasticity, and he happened to live, he overlapped a little bit the time of Isaac Newton. But he was a senior scientist when Isaac Newton was a young whippersnapper. But Isaac Newton was a brilliant young whippersnapper, and he made all sorts of people mad, including Robert Hooke, because he criticized some of Hooke's work, because Newton operated at some level way up here that us mere mortals couldn't even understand. And Hooke and Newton didn't get along too well. But anyway, Hooke was still a good scientist. Okay? And one of the most basic principles related to elasticity of solids is Hooke's law, named after Robert Hooke. And I'm going to write it on this slide, even though it doesn't have anything to do with it. Here's what Hooke's law says. The force applied, the ratio of the force applied to the amount of distortion is equal to a constant. Or the other way of expressing this is F is equal to K delta L, which normally, most of the time when you see it written, is X, not delta L. But we're going to call it delta L because our book does. Okay? And Hooke's law says the ratio of the force applied to an object to its change in length resulting from being either stretched or compressed, like we just did in this previous example, by the applied force, is constant as long as the elastic limit has not been exceeded. Okay? And that's going to lead us to the next slide. Oh, man. Here is, if you think of Hooke's law, the applied force is F, and the distortion, you might say, the amount of compression or stretching, either one, is your delta L. Now, most of the time, I think of the applied force should be on the horizontal axis and the delta L be on the vertical, because the applied force is the action and the delta L is the reaction. But they always do it this way, which is fine. Okay. Now, what this is saying is, if you apply a little bit of force here, you're going to distort it a little bit. Apply a greater force, you're going to distort it even more. A greater force, even more. A greater force, even more. Now, think of this as a spring. Okay? Say you have a pretty sturdy spring here. You pull it a little bit of force, and you go stretch it a little bit. Then give it more force, and you stretch it a little bit more. But it's pulling back on you harder. More force, and you stretch it even more. More, you stretch it even more. Now, it can be compressing, too. The spring is like this, and you compress it a little bit of force, a little bit of compression. More force, more compression. Either way you want to do it, okay? But at some place up there, you're going to stretch, usually with stretching, stretch it a little too hard, and it doesn't come back. That's called the elastic limit. The point past which the material does not return to its original shape. Remember, that was the property called elasticity, and once you pass the elastic limit, it doesn't come back. Okay? Frankly, I would have put it down here, but they put it up here, and they almost always do. After that, it becomes what they call plastic. Okay? Now, I don't know if any of you remember the old commercial for a brand of cars they built up in Tennessee many years ago called the Saturn. Remember the Saturn cars? Yeah, I remember the commercial of the dad working on something out in the yard, and the boy was out there throwing a ball around and threw the ball into the side of the car, and it pinged the door in, but then it came right back out. That was elastic. Okay? But you can probably easily imagine if he had thrown the ball a little harder, or if it was a little heavier ball, going faster or something, at some point it'll hit the car, fall off, and it doesn't spring back. You pass the elastic limit. So this is what they call plastic region, where you've deformed it and it doesn't come back. That's called a dent, okay? I took my car to the shop last Friday for its routine maintenance. It's a fairly new vehicle, so we still have it taking it to the shop to get them to do it, so it all goes on record in case there's anything wrong, you know, that kind of stuff. And the guy said, "Hey, you've had some hail damage." I hadn't noticed it, but there are little dips in the roof and the hood where, I guess, hail hit. I don't even remember when we had any hail. Now, I wondered about it at the time. We have a big old white oak tree in right by our driveway, and that has some pretty good sized acorns on it. I'm wondering if that's not what caused it. But it didn't do any damage to the paint. I said, "Is that going to harm anything?" He said, "No." I said, "It's just aesthetics." He said, "Yes." I said, "I'm not big on aesthetics. We'll let it go." He thought I could get the insurance company to pay for it, but why make them pay for something that's not making any difference anyway? Now, if you keep applying a force. Even after you've reached that plastic region, you keep applying a force, at some point that's going to fracture. Okay? It will actually break. Now there are some materials, we talked about this, no, maybe not, I don't know, that are very brittle. And you may apply a force to it, and it, for a little ways it's elastic, but then all of a sudden it fractures before it ever reaches the elastic limit. That's called a brittle object. Okay? We're not going to go into that yet. This region here, we're in Hooke's law. Okay? Past the elastic limit, Hooke's law doesn't apply anymore. Okay? Oh, and I didn't say anything. Okay, sorry. I didn't say anything about this little symbol here. They mentioned it in the book, but I forgot to say anything. That symbol there is a delta. And didn't we hit this back in chapter 5? Delta means difference. The change in length. Difference in length. So you've added you stretched on the spring, so you changed its length. That's the delta L. Final minus initial. Okay. And that leads us to example 2, which I don't think they have in the slide set. So I think I'll leave it there and go back to the white page. Okay. All right, example 2. A force of 5 newtons, 5.00 newtons, that's a force, is applied to a spring whose elastic constant, that's the K, is 0.25 newtons per centimeter. Okay? So that force is applied to a spring whose elastic constant is 0.25 newtons per centimeter. So the K, Newton's constant, elastic constant, is 0.250 Newton per centimeter. Okay? Now, find the change in length. What we're looking for is the delta L. What was our formula? Oh, I was going to turn back to it, but I've already erased it. Okay? The formula is this. F over delta L, the ratio of the force to the change in length, is that elastic constant. Okay? So we know this, we know that, we're looking for this, so let's solve for delta L first. How do we do that? Look at the problem. How do we get the delta L by itself? One thing we don't like about it, it's in a denominator. We don't want it in a denominator. We want it in a numerator. So how do we get it in a numerator? Anybody? Multiply both sides. How do you undo division? You multiply. Okay? Now it wipes it off on this side, and it moves it over here. So now we have F is equal to K times delta L. Okay, we know this, we're looking for that. We want it by itself. So how do we get it by itself? How do we move the K? Hint, K is multiplied by delta L. How do we undo multiplication? Dividing. So let's divide both sides by K. Got to do everything to both sides. So now you wipe out your K's here, and you have delta L is equal to F over K. Well, let's see if that works unit-wise. F is 5.00 newtons divided by 0.250 newtons per centimeter. Well, the newtons are going to cancel out, and that leaves you 1 over centimeter, which is centimeters. So yeah, that's going to give you centimeters. That's a good delta L. And what's that value? I'm going to cheat a little bit and show you this way. I'm going to move this decimal 2 places to the left, move that one 2 places to the left. How many times will 25 go into 500? Well, I know it'll go 2. 25 will go into 50 twice, 20 centimeters. Okay? Now, say again?
What did you just do? You moved it to
Okay.
2 spaces to the right. And then
Yeah.
down 5.
Yeah, I did it through the 0.25 because I don't like dividing by decimals. So I made this 25 down here. But if I move this decimal 2 places here, you have to move this decimal 2 places there. So now I've got 25 into 500. The 25 will go into 50 twice and then bring down to 0. 20.0 centimeters. Or the other way to think of it, how many quarters are in $5? You got four quarters in each dollar, and 4 times 5 is 20. So 20. I usually like to think in terms of food or money, and most of the time I like either one of them. Okay. I like food better, I think, though. Okay. But I couldn't think of a good food exercise here. So you change the length by 20 centimeters. And they have a little diagram there showing that newtons divided by newton over centimeter is the same as newton times centimeter over newton, and the newtons cancel out, and that leaves you centimeters. Exactly what we did. Okay? Ready for example 3? Or do you need that a little bit longer? Huh? Ready? Okay. Take as much time as you need. Okay. I was making sure this wasn't the same problem. Okay. It's a similar type problem. A force of 3 pounds, different because it's dealing with U.S. customary. So here we have a force of 3 pounds. F is equal to 3.00 pounds. Very precise. Okay. 3.00 pounds stretches a spring. So that's going to be your delta L of 12 inches. Okay. Stretches a spring 12 inches. That's a pretty weak spring, isn't it? 3 pounds is just not that heavy. It's going to stretch that spring. That's almost like a slinky, but probably a little bit better than a slinky. Okay. The next thing says, what force is required to stretch it 15 inches? So F2, let's call this F1. Let's call this delta L1. F2 is going to be the unknown force, and our delta L2 is going to be 15.0 inches. Okay. Now, I know a lot of people, when they go to do a problem like this, try to set it up and go as a ratio. And actually that, I think, would work. But I believe how they want you to approach this one is find the spring constant first. This first thing here allows you to find the spring constant. Because what's the formula for spring constant? F1 over delta L1 is equal to your spring constant, or your Hooke's law constant, or whatever you call that. Okay. So this, we have 3.00 pounds, that's the force, divided by 12.0 inches, that's going to be your K. Now, most of the time, we measure K in pounds per foot, but it's okay to measure it in pounds per inch. And that's going to be, if I'm doing my math right, 0.25 pounds per inch. Okay? Now, Now that we know the spring constant, we can use it over here and say that F sub 2 divided by delta L sub 2 is equal to K. Now we know K. They told us the delta L2, so we're looking for F. So how do we get this? How do we isolate that F? The delta L is on the bottom. How do we undo that? No, it's already dividing. You undo it by, how do you undo division? Multiply. Multiply both sides by delta L2. Delta L2. Okay? So now you got F2, the new force, is equal to your spring constant, 0.25 pounds per inch times delta L of 15.0 inches. The inches cancel out, and that gives you a force in that. And a quarter of 15, I think, is going to be 3.75 pounds. Check me on my math. I'm doing it in my head. Wait a minute. Oh, no. I was looking at the wrong problem. Whew. Yes, 3.75 pounds. I said, how could I be off that much? Okay. Make sense?
What I get confused on.
What's that?
When I have the X out, like when you're Xing out the inches, you take out both sides, and then it leaves the pound. Sometimes I just get confused on which way to go.
Okay.
See?
Oh, like that?
Right.
Yeah. Well, you see, a numerator will wipe out a denominator. If they're both in the numerator, that makes it inches squared, which is not what you want. You want the inches to go because forces are measured in pounds. So that helps you know that's what you had. Whereas in that first one, you had a weight in pounds, or a force in pounds. You had a delta L in inches. That gave you a K in pounds per inch. Okay, because you took the pounds divided by inches. That gave you pounds per inch. Okay, so let the units fall where they may, but be sure they give you the right things you're looking for. Like this, if you're looking for force, wind up in pounds, yes, we think we've done it right. If you wound up with pounds, inches squared, or inches per pound, or something like that, those are wrong units. You did some operation wrong. Units are your friends. They will help you see whether you got the problem set up right or not. And these worked out nicely. Okay. I don't know, did that help any? Okay. Good answer anyway. Okay. All right. So let's move to example 4. Can I erase this one? Yay or nay? All right. A support column is compressed 3.46 times 10 to the minus 4 meters. Okay, so here's your support column here. And when you put this really heavy, massive weight on it, it's going to compress that. Make a delta L of, pretty small amount, 3.46 times 10 to the minus 4 meters. It's not very much, folks. Let me go back to show you about what we're talking about. I don't have a dime on me, but I've got a penny. The thickness of that penny is about 1 millimeter. Okay? A millimeter is 10 to the minus 3 meters. So this big, heavy mass you're putting on here is compressing it just about 3/10 or 4/10 of that distance. It's pretty small. You probably wouldn't even notice it, but it is compressing it. Okay? But that weight, here's your F sub W, that's causing that, is 6.42 times 10 to the 5th newtons. Okay? Said another way, that's 642,000 newtons. Okay? That's a lot of newtons, folks. And it's compressing that less than the thickness of a dime. Okay? Okay. A support column is pressed under that. How much is the column compressed under a weight of 5.6? So this is your weight 1, and this was compression 1. They're asking how much will be the new compression when your weight 2 is going to be, excuse me, about 9 times greater. 5.80 times 10 to the 6 newtons. So you're going to put even more weight on it. Pile another block on here, okay? Okay. How much is the column compressed then? So now we're asking what's your new delta L, your number 2 delta L. That's the unknown. How would you begin?
When you multiply that 6.42 times 10 to the 5th.
Multiply it by what?
By 10 to the 5th newton.
Okay. Okay. That's a number. Okay, that's just a number. If you wanted to express it in how many newtons, just move the decimal 5 places, and that's 642,000 newtons. If you want to write that big old number down, this is just a lot easier to write it, 6.42 times 10 to the 5th. Okay? But what we want to do, we first need to know our elastic constant, which is F sub W1 over delta L1, that's going to be your K. Because it's the same column you're going to do over there too, so it's not going to change. That's going to be your K. So we're going to divide 6.42 times 10 to the 5th newtons by 3.46, I'm having trouble reading my writing, times 10 to the minus 4 meters. Okay, and that's going to give us our K in newtons per meter. Because you see, that's how it's set up, newtons per meter. It's exactly how you measure your K. So someone punch that in on your calculator. Now remember how you do it on your calculator. 6.42 EE or EXP. Don't do times 10. Just 6.42 EE or EXP 5. Divided by 3.46 EE or EXP. Don't ever do the times 10. EE or EXP minus 4. And then you press equal. Now I'm going to make a guess at it right now. I'm going to guess that's coming out about 1.9, 1.8. I'm going to say 1.9. This is a guess. Times 10 to the 9th Newton per meter. You punch it on your calculator, see what you get. 6.42 EE or EXP, whatever your calculator has, 5 divided by 3.46 EE or EXP negative 4. Making a guess, you tell me what you got. 6.42 EE or EXP 5, divide that by 3.46 EE or EXP negative 4. Anyone get anything? Help me, somebody. Dire need of help. Anyone got anything yet? My answer may be off, huh? What you get?
It'll be 1.86.
1 point what?
86.
1.82? Is that what you said?
86.
I can't hear you.
6. 1.86.
1.86. Okay, I wasn't too far off. 86. Do you have an exponent?
10 to the 9th.
Is it to the 9th? Is that what you said? Ah, I wasn't too far off. Newton per meter. Okay, I was guessing 1.86, not bad. Okay? Now, that's your K. Now we have enough information to do this. F sub W2 over delta L sub 2 is equal to K. Same K. This time we know this one. We know this one. We're looking for that one. This we know, that we know. So how do we solve for delta L2? What's wrong with it? It's in the denominator. We want it in the numerator. How do we get it there? How do you undo division? Help me, somebody. Multiply by delta L2 times delta L2. Oops, not squared, 2. Sub 2. Okay. Now. Oh, that's not what I wanted. Okay. These delta, yuck! I wanted my pen. I didn't want to wipe it out completely. These delta L's go out, so that gives us, and this is what we're looking for. Now we want to divide both sides by K, because you undo multiplication by division. And now the K's will go out over here, and you get delta L2 is equal to F sub W2 over K. And we already know what the K is. All right, your FW2 is 5.80 times 10 to the 6th newtons, divided by your K was 1.86 times 10 to the 9th Newton per meter. That's an ugly meter, okay? Still pretty ugly. Let me see if I can clean it up a little bit. Too much. Okay. It's getting too crowded here. And what does this give you? 5.80 divided by 5.80 or 5.8 times 10 to the 6 or EE/EXP 6 divided by 1.86 EE or EXP 9. I'm going to guess that's going to be something about like 2.4 maybe. I'm guessing. Times 10 to the minus 3. 3 point, okay. Say that again. 3 point what? 12 times 10 to the minus 3. Minus 3, and that will be, the newtons cancel out, and that would be meters. So now we are compressing it about the thickness of 3 millimeters. I thought I had another penny. I do. So that would be compressing it about like that, because you added quite a bit more weight to it. So it's going to compress it that much. Still not a lot, but it is. And what they get in the book, look at that. 3.12 times 10 to the minus 3 meters, or you could write that is 3.12 millimeters, because milli is a thousandth, and 10 to the minus 3 is a thousandth. All right. Now, the ancient Romans, Mesopotamian, Chinese bridge builders used to always use stone to build bridges. Pretty good. Okay? But then during the Industrial Revolution, an English engineer, Abraham Darby, built the first cast iron arch bridge. Okay? It made a better alternative to the expensive and heavy stone arch. In later years, however, problems with cast iron bridges became evident because cast iron is pretty brittle under tension, and it would cause fractures and break. So in the late 1900s, an American engineer, James Eads, constructed the first steel arch bridge over the Mississippi River, and that is not much stronger under compression than iron, but more than twice as strong as iron under tension and shearing stresses. So the steel is used for beams and cables in all bridges today. The picture shown in your book is the old Darby's cast iron bridge constructed in Coalbrookdale, England. So let's see if they have that. I don't think they do, but let's see if they do. Let's get out of this slide and see if they have that one in the other slide set. Yes, there it is. We'll go from current slide. There is Darby's bridge. That bridge, they said, was built in 1779, and it looks like it's still operating today. Pretty good. Okay? And they do mention that what they do use nowadays is what they call pre-tensed concrete. They put tension on steel rods, pour concrete around them. When it sets up, then release the tension, and that holds for a really strong bridge. Okay, so our buildings also. Problem set 12.2, do any of the odds 1 through 9 and any of the odds 11 through 19. 12.2, properties of solids, that was one long section. Okay? And I think we're just about out of time, aren't we? Yay or nay? Don't you rest? We're still going till 7? Not yet. Okay. So we'll begin next time with properties of solids. And I don't even have anything to erase. So I'm just going to remember properties of solids. Oh, properties of liquids is where we'll begin next time. Okay? All right. Good deal. Thank you so much. I wish I'd have gone over and got it so you wouldn't have to walk. Okay. All righty.
I'm trying.
Yeah. So y'all have a good weekend. We'll come back next week and only meet one day, Tuesday, and then we have Thursday off. So then we'll get back to 2 a weeks. All right, good deal. Have a good weekend.